Are you there? Are you people there?
Yes, sir.
Okay, good. Okay, so you know that n tuples, which you have already read in your Maths 1, Maths 2, that can be written as x1, x2, x3. Suppose your x is an n tuple, x1 to xn. Write down. Write down, everybody. You take your register, pen. Have you written the n tuple x? Yes. Hello.
So what we have to write? It's not clear.
Write down n tuple x, x1 to xn. You have read your the vector with n component. In your Maths 1, Maths 2, you have seen or not? Yes, tell me. Did you understand? Did you understand what I am saying?
I forgot, sir.
Write down x equal to. You cannot forget this anyway. You will remember it. Write down x equal to, in the two brackets are there inside, x1, x2, x3. If a vector is there, how will you write that triple vector in 3 component? Yes, Snehbandhu.
Write in ijk components.
No, not that vector. IJK component, which you have read in your Maths 1, Maths 2, not in vector 1.
Vector space.
Vector is space, that's right. x1, x2, x3, and so on, xn. You write that like this? Yes or no?
Yes, sir.
Write one vector x, another vector y. y1, y2, yn. Should be written?
Yes, sir.
So what is y transpose x? Y, these are column vectors. So what is y transpose x?
x1 y1 plus x2 y2 plus x3 y3.
So it is, I may write that summation xi yi. Is that right? Summation xi yi?
Yes, sir.
Okay, good. So this is what I require, and actually this y transpose x is called the inner product of x with y. So since it is not taught, so I'm going to tell you from the basic one. So once you understand y transpose x, everything is. Do you remember that Cauchy-Schwarz inequality? Do you remember Cauchy-Schwarz inequality, which you have used in your maxima minima for 2 variables? Yes, Kamlesh wanted to say something.
Yes, sir.
Tell me, have you do you remember that Cauchy-Schwarz inequality? That magnitude of this sum, summation xi yi,
Yes, but I don't remember the expression.
Is less than or equal to, I will show you on slide also, don't worry, summation xi square whole to power half into summation yi square whole to power half. Okay, I will show you once I will reach at that place. So now let me start. So at this position, that Tn plus 1, we have got that h into this quantity into f, h square into this quantity, and then h cube, and then its coefficient is there. We have taken 1 minus gamma 1, gamma 2 is 0, so this h coefficient is gone. 1 by 2 minus alpha gamma 2 we have taken to 0. 1 by 2 minus beta gamma 2 we have taken to 0, right? So this h and h squared term has already gone, right? Yes or no?
Yes, sir.
Okay.
Yes, sir.
So remaining term was only h cube term, that error term, right? So I will just write down this coefficient of h cube as CFR. I think I have used this notation. Yeah. So CFR, I am writing that coefficient of h cube. Just a notation, you just understand this, nothing else is there. I have just rewritten it so that Tn plus 1 can be written as CFR2 because all the coefficients of f, they depends on gamma 2 only. The way you have seen on the last turn that everything depends on gamma 2 because the way we have got the gamma 2 was the free variable, because we have written that gamma 1 in terms of gamma 2, alpha in gamma 2, beta in gamma 2. So everything is function of gamma 2, gamma 1, your alpha and beta. So that if you see this C part, this coefficient of h cube. So if you leave this f part, so the coefficients of this fxx, it is the dependent on gamma 2. Here it is dependent, beta is there. Beta again, alpha, beta both can be written in terms of gamma 2. So everything is basically dependent on gamma 2. So basically, this coefficient h cube coefficient depends on f and gamma 2 only. That's the reason I have written the notation that Cf gamma 2. So this is the coefficient, and then you can put the value of alpha, which you have there, value of beta, I think 1 by gamma 2 or 2 gamma 2, 1 by 2, alpha equal to beta equal to 1 by 2 gamma 2. Put that here, it will be only in terms of gamma 2. So your CF R2 can be written only in terms of gamma 2 and F as some derivatives of F. Is this part clear? Is this part clear?
Yes, sir.
I haven't done anything. I have just rewritten it. Nothing else I have done. Right? Now, let me write two vectors. One vector is your C1F. Another vector is your C2 gamma 2. One is completely depends on gamma 2. First one depends completely on F or its derivatives. Second one depends on only gamma 2. So I have taken C1F as the F part. For example, with this coefficient, your Fxx is there. So this is the first component. Second one will be Fxy F. So here it is written. Third is your Fyy F square. So this is written here. Fourth is your Fy Fx. So Fx Fy. So this is written here. The last one is Fy square F. So this I have written. Right? And then gamma 2 part I have written separately. Fxx coefficient I have written in C2 gamma 2 as the first component. Second term coefficient in terms of gamma 2, that I have written as the second component. Similarly, third and fourth and all these are written, and these are transport, means it is the column vector. C1F is a column vector just like your X. C2 gamma 2 is also a column vector just like your Y. Is this clear to everybody? Is this clear to everybody?
Yes, sir.
What is C2 transpose C1? C2 transpose or C1 transpose does not matter. So what is C2 transpose C1? Can anybody tell me? Quickly do that. Will see F gamma 2 or not? C2 transpose C1. I want answer from you people.
That would be fxx into 1 by 6 minus 1 by 8 gamma 2 plus
No, is it the
fxy.
same as the CF gamma 2? 1 by
Yes,
6, right? So C2 transpose C1 we can write as CF gamma 2. Adrija?
Yes, sir.
Adrija?
Yes, sir. We can write it as CF gamma 2.
Okay, right. So up to this it is clear to everybody? Up to this it is
Yes.
clear to everybody?
Yes, sir.
Okay. Then after that nothing is left. After that we'll apply this Cauchy-Schwarz inequality. So as I said that I will it is written here also, y transpose x I have written here, summation I running from 1 to n xi yi, and then Cauchy-Schwarz inequality tells that magnitude of summation xi yi is less than equal to summation xi square whole to power half into summation yi square whole to power half. Either there are two forms. One is in terms of norm word is used, another one is the simple form is used. So you better understand this simple form. This squared power half is nothing but norm of x2. Squared power half is nothing but norm of y2. So if you want, you understand that with that. Otherwise, you can understand with only that Cauchy-Schwarz inequality is magnitude of summation xi yi is less than or equal to summation xi squared power half into summation yi squared power half, right? So we'll use this fact, this Cauchy-Schwarz inequality, and apply on this one. CF gamma 2 can be written as C transpose. Here it is written in terms of. So just do a bit of calculation. Magnitude of CF gamma 2. Write down magnitude of CF gamma 2. Everybody, just write down. This is your magnitude of C1 transpose C2, or what will be this? C1 transpose C2. Can anybody tell me? Yes. Anybody can tell me?
Fxx into 1 by 6 minus 1 by 8 R2
So
plus.
all the terms are there, right?
Yes, sir.
Is that right? So this is less than or equal to what? If you apply the Cauchy-Schwarz inequality.
Fxx square plus fxy square.
So
X square.
first let us write C1 we have given what? F part, I think. Is that what we have defined C1? Let me check that. C1 we have defined F part. So this will be F component square whole to power half. Is that right? If we apply Cauchy-Schwarz inequality.
Yes, sir.
So this is what? Fx square plus second term is fxy square f square. Third term is fyy square. It was f square, so that will become f to power 4 plus fx square fy square plus fy square f square whole to power half. This will be in one bracket as it is written here. See, let me put it properly. You see, the first term is written fxx square plus fxy square f square fy square f to power 4 fx square. So all the terms is square. sum and then its power half, right? Similarly, we write this C2, all the components of C2 square and then power half, right? Is that right?
Yes, sir.
Yes, sir.
Now, if you see the C2, in C2, the first component and third component, both are same. 1 by 6 minus 1 by 8 gamma 2. Shall I show that? In C2,
Yes, sir, they're same.
you see in C2, first component and third component, both are same. Means its square plus its square. So it will be 2 times its square. 1 by 6 minus 1 by 8 gamma 2. Right? So this is what is written here. That's it, just to show that. So it is 2 times 1 by 6 minus 1 by 8 gamma 2 whole square plus other terms square. 1 by 6 square is 1 by 36. So there are 2 times. So it is 1 by 36 plus 1 by 36 whole to power 1 by half. Up to this it is clear?
Yes, sir.
Okay. Now we cannot touch F part. I have already told. Otherwise, that will put more restriction on F. But if we write this gamma part as h of, let us take this as h of gamma 2, and if we minimize this for gamma 2, then our job is done. Means we'll have minimum, and this is just a function of one variable. Maximum minima of function of one variable, that is your gamma 2. Is that clear? Is that clear?
Yes, sir.
Yes, sir.
Let me let me recall those things. I don't know whether you people have read that again after class or not. What we wanted at that, we have got the local truncation error. There were since gamma 2 was a free variable, so there were several second order methods. The point came that can we get the optimal method or not? So the question comes that we cannot touch F part, but we can somehow minimize your gamma 2 so that we can get up to that extent we can get the optimal second order Runge-Kutta method with 2 parameters, with those your gamma 2, gamma 1 and your alpha and beta, four parameters. Is that right?
Yes, sir.
Okay, so we'll minimize this. So let us take h of gamma 2 as this, whatever the function of gamma 2 we have separated out. Using this Cauchy-Schwarz inequality, we have just separated it out so that our job is easy. We have to just minimize this h of gamma 2. So for minima maxima, the very first thing is that its derivative equal to 0 with respect to gamma 2, right? This is what is this you have read in your 12th standard at least, if not the 10th standard.
Yes,
For
sir.
maximum minima, we require its derivative has to be 0. So we'll just find out its derivative. I have written it very beautifully so that everything should be clear. So its derivative is 1 upon, since power half is there, you can understand that 1 by that minus power half will come. So this is what is written. So it is your 1 by 2 into square root of the same quantity, right? And then the derivative of this. So that beautifully written here. You can verify this, right? So I'm leaving this as an exercise, just that you verify that its derivative can be written in this form. Now, from the derivative, it is clear that h prime of gamma 2 is 0 when this quantity is 0 and this quantity is 0. This quantity is 0 gives the same thing what this quantity means 1 by 6 minus 1 by 8 gamma 2 equal to 0 gives the exactly the same thing what 1 by 3 minus 1 by 4 gamma 2 equal to 0. So basically we get that gamma 2 equal to 3 by 4. Is that right? Is that right?
Yes, sir.
Now, I'm leaving further one thing as an exercise, that verifies that at this point we'll get the minima. Right? At this point, gamma 2 equal to, so you just go for the second derivative, put this value, check it whether it is giving the minima or not. Right? Shall I leave this as an exercise?
Yes, sir.
This is a simple job. You can do that. It is just a maximum minima of one variable. Right?
Yes, sir.
Okay. So gamma 2 is 3 by 4, which will provide you the optimal second order Runge-Kutta method with these 4 parameters, right? And optimal up to that thing, that up to the that coefficient of f terms are minimum up to that. So with your gamma 2 equal to 3 by 4, we'll get that gamma 1 is 1 by 4, alpha and beta is 2 by 3. You can put that value in those equations which we already have, right? So alpha equal to beta equal to 1 by 2 gamma 2, so immediately you get 2 by 3, and gamma 1 is 1 minus gamma 2, immediately you get 1 by 4. Very simple. So the method, if you see, it will be of this form, that yn plus 1 equal to yn plus h by 4. Your gamma 1 is 1 by 4, so h by 4 f xn yn plus gamma 2 is 3 by 4, so it is 3 by 4 into h f of xn plus 2 by 3h, comma, the second component will be yn plus 2 by 3, that is your beta, 2 by 3h f of xn yn. So this will be your second order Runge-Kutta optimal method. Now this can be written in terms of the standard one, that we take this k1 as h into f of xn yn, k2 as h into f of xn plus 2 by 3h yn plus 2 by 3 k1, then yn plus 1 can be written as yn plus 1 by 4 k1 plus 3 into k2. In other words, the standard form normally you will find in the book that yn for RK method, yn plus 1 equal to your yn plus w1 k1 plus w2 k2. In your book you will find this thing. W1 is here 1 by 4, W2 is 3 by 4, and then K1 and K2 are defined here. Is that clear? Is that clear?
Yes, sir.
One more thing that we have already seen, that with these four parameters, these are explicit methods. All the things you can evaluate on the right hand side. It is fxn yn, it is fxn plus 2 by 3h, yn plus 2 by 3h. So for yn plus 1, everything is explicit on the right hand side. So you can calculate this is your explicit second order optimal Runge-Kutta method. Is that clear? Is
Yes,
that
sir.
clear to everybody?
Yes, sir.
Okay.
Yes, sir.
Now, good. So with the different values of, further I tell you that with the different values of your gamma 2, you will further get different second order RK methods. Take gamma 2 as 1 by 2, so you will get gamma 1 as 1 by 2, alpha equal to beta equal to 1. So one method you will get that by writing K1 and K2 suitably, yn plus 1 by 2 of K1 plus K2. If you take gamma 2 as 1, then you see that gamma 2 is 0, only one term is there, alpha equal to beta equal to half, and you get that yn plus 1 equal to yn plus K2, and then K2 is further dependent on K1. So basically you have again the K1, K2, W1 and W2, right? So different methods. This one is called, the second one is called the modified Euler method. So I will give a list of that, maybe later on we'll talk about that. So this is, we have discussed about explicit second order Runge-Kutta method. Is that clear now? Is that clear?
Yes, sir.
Okay. Now, one thing you have noticed, what we have done, that you must understand. What we have done? We have written yn plus 1 or u, whatever is that, yn plus 1 in terms of yns. We have written right hand side also in terms of yns. Everything on the both side, means left hand side and right hand side, what we have done, we have written in terms of yns. Is that clear?
Yes,
And
sir.
then after that, what we have done? After that, what we have done? Anybody? After writing in terms of yns, then what we have done? Snehbandhu, Adrija, anybody?
Like we have just written values in terms of K1 and K2.
No, actually you have collected the coefficients of constant term, coefficient of h, coefficient of h square, coefficient of h cube if you require, right, depending on that, and then you have compared both the sides. Here you have make it to 0, that coefficient of h and h square, which you could do, but h cube could not do because of 1 by 6 coefficient, 1 by 6 term was there, which we were not able to make to 0 because 1 by 6 was there, which we cannot make to 0, right? The similar thing we'll do every time, that we'll write the Taylor expansion in terms of yns, yn is there or un is there, whatever is that, and then collect the coefficients of h, constant terms, h square, h cube, depending on the order of the method, will make this coefficients to 0, and whatever is coming, the some equations you will get with the parameter, as many as parameters are there. If you get those many equations, fine, you can get the unique solution. If you are not able to get those many equations, as you have seen in the second order method, you will get that infinite many methods, and then you have to look for the optimal method if it is possible. Is this point clear or not? Because the same thing you have to do for the problems as well. Once it is asked to find the order of a method. Is that clear?
Yes, sir.
Okay. Now, next we'll move to the implicit method. So first let me close this slide and then so whether the new slide is seen on your screen? Can you see
Yes,
the new
sir.
slide? Okay. So now next we'll talk about your implicit method. Next we'll talk about implicit method. There is one thing which I noticed, that only 1 or 2 students are responding to my questions. So it should not happen. So you please do that, otherwise accordingly your TA marks will be affected. Okay. So you see, I have written that uj plus 1, it should be u prime equal to f instead of y prime. the differential equation. So I have written that uj plus 1 equal to uj plus w1 k1. Only two parameters, w1 and k1. K1 is given by h f of tj plus c1h uj plus a11 k1, means your it is an implicit method. You see, k1 has to be evaluated through k1. It's k1. K1 has to be evaluated through k1, means both the sides has k1, means it is an implicit method. And the parameters here are c1, a11 and w1. Is that clear? Only three parameters. Is that clear?
Yes, sir.
Now, so we have to find these parameters w1, c1 and a11, and see that what order method is that we are getting. It is basically we will get second order implicit Runge-Kutta method, and here you see the number of parameters are less now. So with that less number parameter, means only one evaluation of your slope, that is your k1, without calculating k2, the another slope with the two slopes, because as many as calculations are there, the cost of that method increases, right? So, but there will be another thing that this is an implicit method, so you cannot calculate your k1 explicitly even after finding out this c1 and a11. You have to apply what? You have to apply Newton-Raphson method to find the k1, starting with some initial guess to k1 and then proceed further, right? So let us see. First let me see that implicit method, the Runge-Kutta implicit method of second order. So as I have said, we'll just write the Taylor expansion in terms of UTJs on both the sides, put it there, and then collect the coefficients of constant term h square and see what is happening, right? So the same thing I have written here. uj plus 1, utj plus 1 is your utj plus h u prime tj plus h square by 2 u double prime tj plus so on. Other terms are there. I'm not writing here. And you know that u prime, you know that it is f, u double prime, you know that ft plus f into fu, all these things. So everything is known to you. So I will just rewrite it. Utj, this equal to utj plus h, f of tj, utj plus h square by 2, ft, f plus f into fu evaluated at tj plus capital order h cube. Next term is capital order h cube term. Now, since k1 is an implicit function, so to have the Taylor expansion of k1, we have to do it separately so that there should not be any mistake. So let us see. K1 is written as h f of tj plus c1h, comma uj plus a11 k1, right? This is two components, so we will apply the Taylor expansion of two variables. So it will be f of your tj, uj, the first term, h I have taken out. So next term is your c1h, and then your ft, right? And then second term is a1 k1 fu. So this is what is written, and so on, evaluated at the point tj, right? Up to this it is clear to everybody? Up to this it is clear to everybody?
Yes, sir.
Okay. Very careful. You should be very careful. You have to see the all the terms are coming or not. So this is your, we just take it out, h into f that I have written here, plus c1 h into h, that will be h square ft, and then your a h times a11 k1 fu plus order order h cube. You see, k1 is also of the order at least h, that you can see directly from here. So further you have to put the Taylor expansion for k1, right? So this as the first term, second term, third term is your h into a11 and k1 fu. So I have written h into a11 fu, and then k1 is written as h into f of tj plus c1h comma uj plus a11 k1 plus capital order h cube term. So you see the next term. Till now I haven't done anything except for that writing the value of k1. Now next everything is same. We'll just see the k1 part. So it is h square a11 fu h square a11 fu, and then we'll expand this f of tj plus c1h uj plus a11 k1. So it will be your f of tj uj plus the same, I mean the same that expansion we have to write here, plus c1h ft plus a11 k1, and then your fu plus capital order h cube term. This h square is out. We are not going beyond h cube term. Keep that in mind. So now let us see. So first term is your h into f, second term is c1 h square into ft, third term is, if you see, h square a11 fu f. So h square a11 fu f. Third term, since outside h square, inside it is h is there, so that will be h cube. So this basically this is going to h cube, if you see. So h cube and then c1 ft, a11 is out, so a11 c1 ft fu. So all the terms are written here, and then second term is also written. So that will be your here k1 is missed. That k1 is missed here. So you make this correction just before the fourth equation. A11 it should be k1 fu into f. It should be both. I think a11 is square. It will also be there. This is immaterial because this is going to order h cube term, so this will be absorbed in this, into this. So basically up to this we get, and then order h cube term. Up to this h square a1, so up to this we'll get only h square term, and after that we'll get order h cube term. So that's the reason k1 is finally written as h into f, that is ftj uj, plus c1 h square. Sorry, it is written h square out, then c1 ft first term, second term is your a11 fu f, remaining is your order h cube term, right? Now we'll put this value of k1. I will just go back, and so you have done all the Taylor expansion. Left hand side Taylor expansion is written, right hand side this k1 we require, other things are uj. So this W1 is a parameter. So everything is now written in terms of your uses. Now we'll just put it back into equation 1. We'll put it back into equation 1. All the values, all the Taylor expansions, and then see what is happening. So it was uj plus utj plus 1 equal to utj plus W1 k1. utj plus 1 I have written here, utj plus h into f plus h square by 2 ft f into fu, which we have written the Taylor expression earlier at the point tj plus order h cube. The right hand side it is your utj plus h w1 f. If I take this, no, it won't be possible. This k1 value I am putting there. So this is your utj plus h w1f plus h square, this quantity plus order h cube term. So see, everything we have written in terms of utjs. Everything we have written, all these are evaluated at tj. This also evaluated at tj. Everything we have got. You just compare. On the left hand side utj is there, right hand side utj is there. If you see the coefficient h, here it is h into f is there. Here it is your h into w1 into f is there. Means w1 has to be 1. Very obvious, w1 has to be 1. Next is your h square term. So here it is h square by 2 ft plus f fu. Here it is h square, ft term is there. So w1 c1 is your 1 by 2. w1 from the first term of h square, w1 c1 will be your 1 by 2. Similarly, if you see the second term, fu into f is there, then again your w1 a11 will be your 1 by 2. So you have got three equations. W1 is 1, W1 C1 is 1 by 2, W1 A11 is 1 by 2. So finally this gives that W1 is 1, C1 is half, A11 is half. So basically a unique solution to these parameters, and that gives your second order implicit Runge-Kutta method as follows, that uj plus 1 equal to uj plus k1, and where k1 is written as h into f, all these values are known, so it will be tj plus h by 2 comma uj plus 1 by 2 k1. Is this clear to everybody?
Yes,
Is
sir.
this clear to everybody? Yes? Any question? Any question?
So like I have one
Adrija?
doubt.
Yes, tell me.
In the so I understood everything, but in the derivation that f of tj plus c1h comma uj plus a11 k1, how we are expecting that to f of tj uj plus c1h ft plus a11 k1?
We have applied the Taylor expansion, so two variable Taylor expansion,
Oh, okay, sir.
that we have already done for the just before this part we have done.
Yes, sir.
Do you remember that?
Yes, sir.
So you just see exactly the same thing is done here also, a Taylor expansion. So basically that's what I said, this whole course is dependent on your Taylor expansion. All the methods, most of the methods you will see that it is developed through your Taylor expansion. So powerful, right?
Yes, sir.
Excuse me, sir.
Ask me.
Uh, Sir, the value for K1, we are going to find it by Newton-Raphson method, right?
Exactly.
Okay.
There is no other. Okay, some time is there. I think around 10 minutes are there. So I think I will directly jump to the problem so that this part will be clear. And then fourth order implicit Runge-Kutta method, that is also there. So that I will not derive the method, but the method it is given in the book, I will directly show that, right? Now, let me go to the problem part. I think it is here itself. Yeah. Whether this slide is shown on your screen?
Yes, sir.
Okay. Same problem. There is a reason to take the same problem so that you can compare the results with all whatever the methods you are developing continuously. You can compare those values, right? U prime equal to minus 2t u square, u0 is 1, h is 0.2. You have to solve on 0 to 0.4. Use the second order implicit Runge-Kutta method, that is uj plus 1. Just now we have seen that. Right? The very first thing is that you have to divide the subinterval, that 0 to 0.4. So that is your 0, then 0.2, that is your T1, 0.4, that is your T2. So your U0, U1 and U2 are there. U0 value is already given as 1. So basically you have to find out U1 and U2. Is that right? Is that right?
Yes, sir. Yes, sir.
Okay, so everything is same. This is the method that K1 is given by this. And so basically K1, if you write, it will be your, by writing in terms of this minus 2t, 2t u square. So K1 will be minus h, 2tj plus h, and then uj plus 1 by 2 of K1 square, right? It is very simple because your f is your minus 2t u square, and it is your h into f of tj plus h by 2, means wherever t is there, tj plus h by 2 it is replaced, and wherever uj is there, it is replaced by uj plus k1, half of k1. So it is minus 2t square, so uj plus 1 by 2 uk k1 square, and tj is replaced by your that thing. So 2 gets cancelled out because I have taken 2 tj. 1 by 2 was there, so that multiplied here, so 2 tj plus h, so that 2 is gone because 2 by 2 that gets cancelled out. So basically, you have to use now Newton-Raphson method. That's the major part, because u0 is known, it is 1. If you get the k1, your job is done, you will get the next value. So f of k1, you have to write in this form. F of k1 is your k1 plus h. You have to take all the terms on one side. K1 plus h into this whole term equal to 0. So your f of k1 will be this quantity, which is equal to basically 0. So put these values, and then h is 0.2. So you just put the value of, once you differentiate, should be very careful that it is you are differentiating with respect to k1. Keep that in mind. You are differentiating with respect to your k1. So f prime k1, that is your d by dk of f, you will get that, right? So your k1 s plus 1, that is the s plus 1 is the s plus 1th iterate value, equal to k1 sth iterate value minus f k1s divided by f prime k1s. You understand that? It will run from s equal to 0, 1 and so on. What will be your initial guess for this? K1 0, to get K1 1, you require K1 0. So very simple, that which is known to you, the basic slope, that is your h into f of tj uj, right? Here it is for j equal to 0 and 1. So K1 0 will be your h into your f of tj uj. Is that clear? This is the nearest one which is available to you. Is that right? That is the major part. What should be the initial guess? Is that clear? Is that clear? Hello?
Sir, I do not understand that why we are taking initial guesses that h into f of tj.
This is the nearest one, and you can calculate that. There is no other value which you can take from this. Either you have to go by somehow you solve the differential equation, linear differential equation corresponding to this, and then if you get some I have already discussed this part. This is the most complicated part, to choose the initial guess for anything, because there is no particular way. Whatever the situation is available there, means the problem, if it is possible to linearize the problem, since all those things are not known to you, so the best way is that the nearest value of k1 you take that, the simplest one, so that is your h into f. That is the only reason. There is no other reason here.
Okay, sir.
What else you can take which is known to you? What else you can take without any knowledge of the problem? Can you imagine something?
No, sir.
So that's the basic trouble. That's the basic trouble. Since nothing can be done, so at least some initial guess you require. So you have to choose the closest one. If h is very, very small, we have already talked, then it does not matter the slope at the two consecutive points, means k11 and then the previous value, right? So it is very close enough. So that's the reason this K10 is taken as your h into ftj uj. There are other ways, but that you cannot understand at this stage. So you may take at for the point 0, it will be your t0 u naught square. T0 is 0, so immediately K10 is 0. With that K10 is 0, you can calculate f of K10, f, and then your f prime K10, and then you can, using your Newton-Raphson method, you can get K11, and then similarly you can get the fk1 k11, f prime k11, and then k2 value, and you can continue this with your Newton-Raphson method. And you have to stop at certain stage. Once you find that the two consecutive values up to certain tolerance, it is close enough, you have to stop at that stage, right? For example, your here it is stopped at K3 only, but you see that it is not matching except for the first decimal place, that is your 0. Here it is 3, here it is 9. So you have to go further, but anyway, just for the demonstration, it is taken like that. So once you get the value of K1, to get the value of U2, right? So again, you see for implicit methods, even though we have got it with less parameter, that second order method, your Runge-Kutta method, implicit method, but we require this Newton-Raphson method, and we have to do the calculations for that. So the number of calculations again increases here. Is that right?
Sir, I
Yes,
had a
sir.
doubt.
You ask me.
In this case, the equation in K1 is quadratic equation. So why can't we just solve for K1 instead of using Newton-Raphson?
I understand that. Suppose it is the problem is not only u prime equal to some coefficient. Here it is -2. The coefficient will change t u square. If it is suppose u to power 1/2, can you do that, Adrija?
No, sir, then it will be complicated.
So
Like
you
for
have
this.
wait. So you have to do the problem in a general way. Definitely, this particular problem you can use your quadratic part. Right?
Okay, sir. Okay, yes.
Just because of the demonstration, I have done in a general way. Because for any problem, if it is power, even power 4 is there, it is not easy job. If it is u to power 4 is there, it is not an easy job, right?
Yes, sir.
Solving fourth order degree equation is not an easy job. Even up to cubic also might create some trouble depending on the situation. Quadratic you can do. So that's the reason I have taken the general way. And if you do, for example, suppose this type of problem comes your exam, and if you do by quadratic one, you will not get the marks, because that is not the way. Another thing is that I tell you one more thing, since you have talked about this. Suppose the two equations are there, or three equations in three unknowns. Suppose somewhere it comes, it will come later on once we go further. Some other numerical methods for your boundary value problems. Then you get this algebraic equation of this type, three equations in three unknowns. If you solve by eliminating the variables, you will get 0 mark. This is taught to you at very early stage, possibly starting from your 6th to 8th standard or so. You have to solve this by Ax equal to B, your Gauss elimination, Gauss Seidel, and all those things, right?
Yes, sir.
That is the advancement which you have read here. The problems are given either in your exam or anywhere for your course. That is just to test whether you understand or not. It is not to test that. Suppose I give that 5 equations, 5 unknowns, or 6 equations. So that is only that tedious calculations will be there. If you see the procedure will be the same, right?
Yes, sir. Got it, sir.
So it's clear. Any other doubt? Anybody has any other doubt?
Sir, one doubt.
Ask me.
Sir, in that we have taken the third iteration of K1, but it is not matching with K2, the
One
second
has to go
iteration.
further. That's right. Except for the first decimal place, it is not matching. So one has to go further.
So, sir,
No doubt.
we have to. Okay.
Depending on your tolerance, if your 2 decimal place tolerance is there, right? That is your 10 to power minus 2 type of thing. You have to go for more ki, the k1s. Only then you can stop at that stage. That is the general way to stop any iterative method. Once your two consecutive values are close enough, depending on your tolerance, second place, third place, fourth place, as many as tolerance is there, accordingly number of iterations will increase. Right? Jai.
Yes, sir.
Okay. Any other query? Any other query? Okay, then for today I am closing at this stage, and we'll meet on Saturday. Okay.
Okay, sir. Thank you, sir.
Proceed further.